Hello and welcome to part D of our four-part video series. And so in this final portion, what we're going to be basically dealing with is the situation where instead of us trying to construct our own system from the ground up and being able to optimize things and know what all of our parameters are to be able to construct our ODEs and do Jacobian linearization for our Laplace transforms into Fourier transforms for our transfer functions, instead of being able to do all of that, what we've been instead handed in this last part is a system that's already been built. And so we have to be able to say, what then? How do we move forward and understand how the system is going to react when it's receiving incoming signals, when we don't know what the system necessarily consists of? Like, what are the differential equations that are running the whole dynamics of the process. And so first, what we're going to do here is generate 50 points of synthetic data for a step response of the previous two tanks that we've been dealing with in series for 15 seconds, and add normally distributed error around each value with a standard deviation of 0.02. Then we're going to fit the data using an FOPTD. So what that stands for is first order plus time delay model, by minimizing the sum square error between the model and the data. So first, let's talk a little bit about the first order plus time delay model, and we'll go ahead and proceed here. And so real quick, we have our two tanks in series. So we have our QC. That's a terrible Q. QC. Now this is our manipulated variable. Manipulated variable. We have our height in our first tank. Then we have our second tank right here. So we've got our Q2. And then here we have, we're determining, we're going to set a set point for the height level in tank 2. So now we have what we've been dealing with in this whole four-part video series is we have our GC, and in this case we're going to be using a PI controller, which we'll get into in just a second. And then we have our process transfer functions. And then we have our outflow. So we've got our, we have our H2 set point going through the error. We've seen all this in the previous videos. The point is we don't know what this consists of. We don't know how it's operating. So what we need to do is we're going to proceed by using first order plus time delay. And so dead time is a killer in systems, and so dead time being there being a lag, and so you kick in your controller response, and it takes a few seconds or maybe whatever amount it takes. The system doesn't immediately respond. You shut off the hot water in your house. You can take a shower for probably a couple more seconds before the water becomes cold. So there's this delay, there's this dead time, and it really can be a killer to optimizing our systems and responding appropriately. And so what we're going to do here is we are going to first, what we need to do is establish some sort of steady state flow, and then we want to generate a step response. So basically we're going to be creating our own experimental data here, and see what happens. How does our system respond to continuous step responses from the initial steady state flow that we determined from QC? And so then that's going to be able to show us a behavior of the process that we can then start to model a fitting to, or fit our model to, I should say. So the reason for a PI controller here is because it's going to allow us to do a integrated time weighted absolute error. So an ITAE. The reason we want to use an integrated time-weighted absolute error is because we don't want to have errors persisting for a long time. If we draw this out here, I'll do it right here. I'll do it on the next page. Keep it fresh. So if we also what we're going to see is we might have a delay, and then the system might then steady out. But this right here, this initial portion, is our dead time between when we kick in for it to do something and when the system actually responds to the initial control. And then what we're seeing here is our KC, our PI, with our ITAE. The way this operates is it is going to be KC multiplied by 1 minus the exponent of negative time minus our dead time over tau. And where time is being evaluated being greater than the dead time. So this is our PI controller that we're going to be using, the function in which it's operating under. And again, just for a PI in general, we have our KC, and then it would be 1 plus 1 over tau I s. So what we're going to do now is we want to be able to have our steady state flow simulate a step response, because then what we're going to be able to do is fit a model of, we're going to give some initial parameter guesses to our data that we see, and then we're going to be able to optimize what those parameters need to be. And the way we're able to optimize it is because people have done just many experiments over many different types of tanks and situations to statistically derive what are the optimized parameters for being able to use this kind of controller. So let's go ahead and shift over to coding. We'll bring this in here. So first is we're going to be experimenting, what did we say, over 15 seconds and 50 points of data. Okay. So NP linspace 0, 15, and 50. We're going to be doing, call it our process here. And the process here is, what we're doing is we're multiplying, right? We said our two tanks, which we've already previously shown here to be, where are we at? They are, the transfer functions are somewhere, here they are. QC to Q2 and Q2 to H2. All right, and now we want to simulate a step response of this process, because we want to be able to see how is the process changing over time with respect to inputs and outputs. And so we don't care about the first response, or not the first response, the first variable, H2, we're going to call it our experimental H2, because we don't know what it is, and we want to determine that. All right, and so now we are going to then put this in here as TF pros step, where T equals T experimental, oops, with an underscore. Okay, now let's go ahead and get some plotting options. We'll take this in, we'll make some deletions. We don't need rows and columns. Our X now is our time in which we're running the experiment. Our Y is our experimental height. We don't need any of this, but we are taking experimental data. So we're going to call it, we're going to put it in markers for our mode. All right, scatter, we don't have a second plot there. We're not doing in logarithm, and I don't know, maybe that's fine. Oh, I gotta run all, okay. All right, so So that's a little bit high, a little bit short. Like that, call that that. Okay, so now what we're seeing here is what we showed over here, which was we're having a bit of a time delay, and then it's going to have a step response that continues to rise until it evens out at a new steady state. And so here we're being able to assess right now, what is our system doing? How is it responding over time based off of changes to our manipulated variable on the front end, and how the transfer functions are relating to any inputs to the system and what they're pumping out as outputs. Now this data looks a little bit too clean, so let's go ahead and fix that, right? We want it to look like actual experimental data. So we're going to bring in a number generator. Oops, random state 1, 2, 3, and we'll call this random number generator. The RNG action here. Now our H2 experimental data is going to equal RNG. What is it? Is it normal? And then we have our location being, what we're doing is we're gonna have our location be the height to the original experimental height in our tank, second tank, and then we're gonna give it a standard deviation of, we said 0.02. So let's go ahead and run the data here. Now this looks a little bit more like we've like what experimental data would look like, where we've got some error in our system. And so the next thing we're going to do now is move forward with our first order plus time delay model, so that we can start to fit a model with it with initial guess parameters, and then being able to optimize those parameters to get our fitting accordingly. All right, so now what we're going to do is we're going to fit the data that we just synthetically derived using our FOPTD model by minimizing the sum squared error between the model and the data. So let's go ahead and do that now. So we're going to define our FOPTD model, which takes in a vector of parameters, and we have our k value, our tau, and our theta. And these are all going to be, we're going to unpack that in our vector of parameters here. Now we have what we showed is our PI, no, not our PI, but our first order plus time delay. And so that we have our k times, it's going to be 1 minus the exponent of, we had minus, let's do it like this, let's do minus, we had our time experiment. What was it? It was minus theta there we go. Oops, there we go, minus theta. And then that was divided by tau. And I think that's good to go for that. So now let's go ahead and return JNP, where we want to get the response now of our system. And so we're looking and evaluating where t exponent less than the dead time and y. Oops, unmatched. What was unmatched? Oops. Okay, now let's we need to return, not return, but we're going to fit a model to it with an initial guess, but we want to, which we can go ahead and give an initial guess real quick. And looking at this, we've roughly got, it roughly evens out around 2, it looks like. Let's do 4 and then a dead time of around 1, maybe. Just eyeballing the original numbers here. So now we need to define our sum squared error, because that's going to be taking the difference between our model at every point from our experimental data, squaring the difference between either a negative result or positive result, and then summing that all up together as a statistical analysis here. And we're returning everything that we just discussed about what the sum squared error is. So we're returning our JNP sum. We're going to sum up all of the experimental data minus the difference between what gets kicked out, I should say. And this gets squared, and then we sum that up. And there we go. Okay. So now let's go ahead and run that vguess equals. Now we need to go ahead and plot this out and see how it fits the data. And let's see here. So we've got our mode. I'm going to add scatter here of FOPTD, our vguess. Our mode now is going to be line, since this is the model that we're fitting. And, oops. There we go. I said lines, it aligns. So here's our initial guess. It wasn't terrible, but you can see that it can definitely be improved upon. And so let's go ahead and minimize the results here, or optimize the results. So we're going to go ahead and call it results, anything that gets optimized here, and we're going to minimize the difference between our sum squared error and our vguess. Don't you like? All right, so it's saying, yeah, there it is. So I just put my letters in the wrong direction. So it's able to run the initial model, but it wasn't actually doing our sum squared error yet. And since we didn't have that as part of our parameters, it didn't matter yet, but it matters now. All right, so we're gonna rerun that. It says it optimized and minimized our results successfully. So let's go ahead and see that. Okay, this is still our initial guess. So we're gonna call our minimized value, we're gonna call that result, and then we want to kick back and see what happened. Okay, so there we have our optimized parameters for kicking off our ITAE and our initial FOPTD, get the letters right in order. And so now what we're going to proceed with is showing the optimal controller gain and reset time for a PI controller. All right, so in order to find our optimal controller gain, ITAE controller gain and reset for time for a PI controller, people have already taken the time and done collected a lot of empirical data to optimize these values for us, which is very helpful. And so first we're going to go ahead and stick these as our results, our optimized results now. Now our controller gain, our KC is our controller gain. Now the optimized data for our PI controller that people have derived is 0.5 for a FOPTD. Is 0.586 times tau divided by theta. Now this is going to be raised to the negative 0.916, and this whole thing is going to be divided by k. And then our reset time, so we've got our tau I equals, and that right here is 1.03 minus 0.165, and then this whole thing is going to be divided by tau, multiplied by tau divided by theta. And we're just running a PI controller, not a PID controller, so our tau D equals 0. And this needs to be tau divided by theta. Okay, so now what we want to do is, now that we've set our optimized PI parameters and control for our FOPTD, what we're going to do now is, with this optimal ITA ITAE controller gain, mouthful, and reset time for our PI controller, we want to now simulate our closed loop response for our two tank in series with this new PI controller that we've optimized. And so not the FOPTD model that we just did. So that's where we've been given a system, the equipment's already in place, the process is already in place, the transfer functions are already in place, where we just did our step response to simulate and empirically derive and assess the changes to the system with inputs and outputs. Rather, so that's what we just did. Rather, with this new and optimized PI controller and the parameters that we've set for our controller game, we're gonna go backwards from things that we set up in previous videos and assess how do these new parameters that have been optimized impact our controller gain with the input coming in, and then how it responds with the output on the back end. And so let's go ahead and start with the first one, which is assessing. So when we had in our response, in our closed loop response, we had changed our standard deviation. Our deviation variables with an increase of 1 from our steady state. And this was how our system had responded, was we had large oscillations to begin with, and they got ever progressively smaller until it stabilized out to around 1. But this took a while, and there was a lot of oscillations in our system. Even though it did stabilize out, it didn't have what we showed where the amplitude ratio is greater than 1 and where it went off on into eternity at ever increasing rates. It did stabilize out and get smaller and smaller, but it took a while, and there's a lot of oscillations. And so now with our new and optimized parameters that we've set, let's go ahead and take out these so it doesn't run interference. All right, and make sure this was run down here. And now let's see how our system responds. So we should see a lot more stability and a lot less oscillations. It didn't, oops, there we go. Now let's retry this. Still didn't like that. What did I do wrong? What did I miss? Ran that. Okay. It doesn't like that. It keeps increasing and doesn't even ever hit 1. Let's go back and see how we set up our PI controller. Oh, look at that. I switched my thetas and my taus. That might make a little bit of a difference here, as in a lot of a bit of a difference. So let's fix that. There we go. There we go. Now let's rerun that in our feedback loop for the closed loop system. There we go. Look at that. That looks a lot better. So here, now with our, previously we saw all those oscillations until it finally reached, stabilized out around 1, and even then it was still oscillating. Here we're showing that if we have an input of our manipulated variable with any sort of deviation variable, this is what the system is going to do. It's going to take in that input, and then it's going to respond with, we get a little bit of a rise above 1.1, a little bit of a dip as it comes back, but then almost immediately it stabilizes out and stays stable. And so this is incredible to see that we were able to optimize our PI controller and know what the settings are needing to be, so that we can take an input, we can change any sort of inputs coming into the system, and not have just this crazy unstable system on the back end. And so that's just remarkable to be able to see how that works. Now the other one is our Bode diagram. And so where we saw earlier in the previous video, we saw there was a phase margin of around 10. And so even though, yes, it did hit the crossover frequency of -180, and it did stabilize out with what we showed when KC was 1. When it was 3, it just went off and was just out of control. But when it was 1, at least, it did stabilize out. But again, it took a little while. And our phase margin was only about 10 degrees. And we did hit that crossover frequency. So let's go ahead and rerun and reassess our Bode diagram. Let's just run all, just make sure I'm not missing any components here. Okay, and so now what is really cool to see is before, where we did hit our crossover frequency, here we never even reached negative 180. Whereas before we did hit it. And when we assess our amplitude ratio in decibels here, right, a log of 1 being 0 here, so at around around 0, having a hard time getting to it. Anyways, somewhere around 0.55, let's just say. If we go down here and assess at 0.55, we have negative 122. So in with our previous settings that we had set, we had a phase margin of around 10 degrees. Here, we've got like 58 degrees of a phase margin. That's incredible. So that is just remarkably more stable when we assess it from our Bode diagram as well. And so we see it visually. I mean, we see how quick the system responds and our closed loop response, how there's just like a little bit of an oscillation above 1, or not even an oscillation, but just a rise above 1, a little bit of a dip below 1, and then he immediately stabilizes out. And it's confirmed also in our Bode diagram, showing that we never even hit our crossover frequency. And when our amplitude ratio would be 0 in decibels, we have a phase margin of almost 60 degrees. And so this concludes our video series, and we really wanted to be able to show how you can just take your linearized dynamics with the Jacobian linearization. We can take our Bode diagram and assess stability for our frequency response analysis, and connecting Laplace transform and Fourier transform, and being able to really show, like, if we have our system and we have our controller and we have our closed loop response, we can bring our transfer functions and multiply them in series, understand and how to connect them together, and then really understand, with depending on what's coming in, we can assess what's coming out and at what ratio and at what phase lag, so that we can then connect the two to optimize really with a stable system. So we can assess if it's going to be stable or unstable, and then unstable by how much, or stable by how much, and then if it is unstable, what we can specifically do to bring about the stability that we're looking for. So I appreciate you watching these 4 videos, and it was a joy to work through this, and I hope you have a good day. Thank you.